let's try to think about this question for a second. Oh, sorry, this is too far to the left. So let's say that the set of solutions to a 3x3 linear system is not just one point. So we don't have a unique solution that we can get this way. What could happen? What do you think could happen? Okay, I see answers number 3 and 5 seem to be dominating. There's also a bit of answer number 1. And in fact, these are pretty good answers. I see even some of you figured out that you can answer 1 and 3 at the same time. Or 3 and 5 at the same time. I yet have to see somebody with 3 hands answer all 3 numbers at the same time. But okay, so indeed, we'll see very soon that we could have either no solution, a line, or a plane. The other answers, well, 2 points, 2 solutions, we will see is not actually a possibility, because if you have 2 different solutions, then the entire line through these 2 points is also going to be made of solutions. A tetrahedron is just there to, amuse you. It's not actually a good answer to that question. It's not very likely that you will get a tetrahedron out of intersecting planes. A plane is indeed possible, and I don't know is still okay for a few more minutes, but we're going to get to the bottom of this, and then we will know. Okay, so let's try to figure out what can happen. So let me go back to my picture. And so I had my first 2 planes. They determine a line. And now I have my third plane. And maybe my third plane is actually parallel to the line, but doesn't pass through it. Well, then I'm afraid that there's no solutions. Okay? Because to solve the system of equations, I need to be in the first 2 planes. So that means I need to be in that vertical line. Well, that line was supposed to be red, but I guess it doesn't really show up as red. And it also needs to be in the third plane, but the line and the plane are parallel to each other. There's just no place where they intersect. Okay? So there's no way to solve all the equations. On the other hand, the other thing that could happen is that actually the line is contained in the plane. And then, well, it means any point on that line will actually solve automatically the third equation. Okay, so if you try solving a system that looks like this by hand, what you will notice, if you do substitutions, eliminations, and so on, what you will notice is that, after you've dealt with 2 of the equations, the third one here would actually turn out to be the same as what you got out of the first 2. It doesn't give you any additional information. It's as if you had only 2 equations. The previous case would be when actually the third equation contradicts something that you can get out of the first 2. For example, maybe out of the first 2 you got x plus z equals 1, and the third equation is x plus z equals 2. Well, it can't be 1 and 2 at the same time. Maybe another way to say it is that this picture is one where you can get, out of the equations you get a number equals a different number. That's impossible. And that picture is one where out of the equations you get 0 equals 0, which is certainly true, but isn't a very useful equation. So you can't actually finish solving. Okay, so let me write that down. So unless the third plane, let's say it is parallel to the line where P1 and P2 intersect. So then there's 2 subcases if the line of intersections of P1 and P2 is actually contained in P3, in the third plane, then we have infinitely many solutions. namely any point on the line, will automatically solve the third equation. Now, the other possibility, the other subcase is if the line of intersection of P1 and P2 is parallel to P3 and not contained in it. Then we get no solutions. Okay, so again, just to show you the pictures once again, when we have the first two planes, they give us a line. And now, depending on what happens to that line in relation to the third plane, various situations can happen. So if the third line just hits, sorry, if a line hits the third plane in a point, then that's going to be our solution. And if that line instead is parallel to the third plane, well, if it's parallel and outside of it, then we have no solution. If it's parallel and contained in it, actually, then we have infinitely many solutions. Okay. So going back to our list of possibilities, that means, well, let's see what can happen. So no solution, well, we've seen that happens when the line where the first two planes intersect is parallel to the third one. That exists. 2 points, well, that didn't come up. Okay, and as I said, the problem is if the line of intersection of the first two planes actually has 2 points that are in the third plane, well, then that means actually the entire line must also be in the third plane. So if you have two solutions, then you have more than two, actually. In fact, you have infinitely many, and we've seen that can happen. Okay, tetrahedron still doesn't look very promising. What about a plane? Well, that's a case that I didn't explain, because I've been assuming that P1 and P2 are different planes and they intersect in a line. But in fact, well, they could be parallel, in which case we already have no solution to the first two equations, or they could be the same plane. And now if the third plane is also the same plane, if all three planes are the same plane, well, then you have a plane of solutions. If I give you 3 times the same equation, that is a linear system. It's not a very interesting one, but it is a linear system. Okay, and I don't know is no longer a solution either. Okay, any questions? Yes?
What's the geometric significance of like x plus y plus z is equal to 1 as opposed to 2 or 3?
Okay, so that's a very good question. The question is, what is the geometric significance of an equation like x plus y plus z, or say this one equals to 1, 2, 3, or something else? Well, if the equation is x plus y plus z equals 0, it means that our plane is passing through the origin. And then if we change the constant, it means we move to a parallel plane. So the first guess that you might have is that this number on the right-hand side is the distance between the origin and the plane. It tells us how far from the origin we are. That is not quite true. In fact, that would be true if the coefficients here form the unit vector. Then this guy would just be the distance to the origin. Otherwise, you have to actually scale by the length of this normal vector. And I think there's a problem in the notes that will show you exactly how this works. Okay? But you should think of it roughly as how much have we moved the plane away from the origin. That's the meaning of this last term, d, that's in the right-hand side of the equation. Okay. So let's try to think about what exactly this case, how do we detect now in which situation we are? Because that's all very nice in the picture, but it's difficult to draw planes. In fact, when I draw these pictures, I'm always very careful not to actually try to pretend to draw an actual plane given by an equation, or when I do, then it's blatantly false. It's difficult to draw a plane correctly. So instead, let's try to think about it in terms of matrices. In particular, what's wrong with this? Why can't we always say the solution is X equals A inverse B? Well, so the point is actually you cannot always invert a matrix. Okay? So recall we've seen this formula that A inverse is 1 over determinant of A times the adjoint matrix. And, well, we've learned how to compute this thing. Remember, we had to take minors, then flip some signs, and then transpose. Well, that step we can always do. We can always do these calculations. But then at the end, we have to divide by the determinant. Well, that's fine if the determinant is not 0. But if the determinant is 0, then certainly we cannot do that. So in fact, what I didn't mention last time is that the matrix is invertible. That means it has an inverse exactly when its determinant is not 0. Okay, so that's something we should remember. So if the determinant is not 0, then we can use our method to find the inverse, and then we can solve using this method. If not, then not.